All right, welcome to the Explainer. Today, we're going to totally reframe the world of chemical reactions. Because let's be honest, instead of just staring at a bunch of boring letters and numbers on a chalkboard, we can actually view this whole thing as an epic drama. Think of chemistry as the ultimate reality show. I'm talking about intense relationships, incredibly messy breakups, bitter rivalries, and some downright dramatic partner swaps. So, to really kick things off, consider this for a second. What do burning a piece of paper, an old rusting iron gate, and cooking your absolute favorite meal actually have in common? Well, they aren't just random, unrelated events. They're actually profound transformations happening right under our noses. Grounding the science in our everyday lives really helps us realize that chemistry doesn't just happen in some sterile lab, it is, quite literally, happening everywhere around us. Here is our exact roadmap for today. We'll start with changes, physical versus chemical. Then, writing and balancing equations. Third is breaking down decomposition reactions. Fourth, the chemistry of relationships. And finally, mastering redox reactions. Section 1. Changes, physical versus chemical. Let's just lay the absolute groundwork for what actually constitutes a chemical change. We all kind of know that our physical world splits into two main types of changes, right? A physical change, like, say, melting an ice cube, alters the state of the thing, but fundamentally it remains the exact same substance. Water is still water. But a chemical change, that alters the actual fundamental composition. What's truly fascinating is how something as simple as a burning candle represents both of these at the exact same time. The melting wax dripping down the side, that's just a physical change. But the actual burning wick, that is a true chemical transformation. Section 2. Writing and balancing equations. Because when a chemical change happens, we absolutely have to document it. You see, thanks to the law of conservation of mass, you can't just magically create or destroy stuff. What you start with, you must end with. No exceptions. So we take these scary-looking complex equations and break them down into completely manageable steps. You put your reactants on the left, your products on the right, and then you just pick one element to start multiplying until both sides are perfectly balanced. The secret here is to treat this entire process like a strict financial ledger. You list out your elements, say iron, hydrogen, and oxygen, and then you compare the reactant side against the product side. Then you just use coefficients to adjust the numbers until they match perfectly. Once the left side perfectly equals the right side, boom, your ledger is balanced. Section 3. Breaking down decomposition reactions. Now, this is basically the chemistry equivalent of a messy breakup. In a decomposition reaction, a single, happy compound breaks completely apart, and it's usually forced to do so by some kind of external energy. If you hit it with heat, it's thermal decomposition. Think of ferrous sulfate crystals losing their bright green color and turning white. If you zap it with electricity, it's electrolytic. And if you use light, it's photolytic, like sunlight hitting stark white silver chloride and turning it into a dull gray silver, which, by the way, is the foundational science behind old-school black and white photography. Okay, real quick trick for you. When you're using electricity to split water, it can be tough to remember which gas goes to which side. Just use this classic memory trick, CH and AO. Cathode collects hydrogen, and anode attracts oxygen. It literally keeps your electrode straight every single time you use it. Section 4. The chemistry of relationships. Honestly, this is where the real, intense drama begins. Here is the golden rule of displacement. A more active element will always displace a less reactive one. Imagine a couple happily minding their own business. Suddenly, a much more powerful, highly reactive element swoops right in and completely steals the partner, leaving the weaker element all alone. It is dramatic, it is cutthroat, and it happens in test tubes literally every single day. So, how do we know who the ultimate partner stealers actually are? Well, we rely on the reactivity series. You chart the elements based on their power. You've got your heavy hitters like potassium and calcium at the very top. These guys take whatever they want. And all the way down at the bottom, you have elements like copper, silver, and gold, which are the absolute least reactive. And that brings us to the next level of the drama. Single displacement is a pretty clean steal. But double displacement? Oh man, that is like two massive sports rivalries crossing paths. Instead of one element getting totally left out, the two compounds completely swap their partners in their teams. Everybody trades, leaving us with two entirely new couples. Now, when these pairs swap in a double displacement, they often leave behind some evidence. They create what's called a precipitate. That's an insoluble solid that just suddenly forms out of nowhere and settles at the bottom. You can literally mix two completely colorless liquids together and boom, instantly get a thick, bright yellow solid of lead iodide. It's a wildly striking visual result of these ion swapping partners. Section 5, Mastering Redox Reactions. This is where two totally opposing forces happen at the exact same time. Think of this as a simple microscopic tug of war. Oxidation means a substance actually gains oxygen. Reduction, on the other hand, means a substance loses its oxygen. Actually, scratch that. Its oxygen is basically stolen away. When both of these processes happen simultaneously in the same reaction, we call it redox, reduction and oxidation. Textbooks absolutely love to overcomplicate how to identify the agents here, so let's just bypass all that and use the swipe trick. First, just figure out who got oxidized and who got reduced. Got it? Okay, now literally just swap their titles. The element that got oxidized is the reducing agent, and the element that got reduced is the oxidizing agent. It is a completely foolproof trick for your exams. All right, before we wrap things up today, I want to leave you with one final puzzle to test out your new chemical detective skills. We already know that when you split water, hydrogen and oxygen collect in a 2-to-1 ratio by volume. But what is their ratio by mass? I want you to think about those atomic weights, apply that strict ledger mindset we talked about today, and see if you can balance out that final equation. Thanks so much for exploring this with me today. Catch you next time.